Imagine reaching the nearest star not in millennia, but within a single lifetime. For decades, the warp drive was pure science fiction, beautiful on screen but hopeless on paper. Every physicist who ran the numbers hit the same dead end. Then a small private lab in Manhattan decided the math deserved another look. In 2024, their team published something extraordinary in a respected physics journal, a warp drive solution with no exotic matter, no impossible ingredients, nothing physics forbids. The internet declared the barrier broken. The physicists who reviewed it were far more careful. Stay with me, and I'll show you exactly what they found, and what it really means for reaching the stars. Now get yourself comfortable, hit subscribe, we begin. In April of 2024, a paper appeared in a respected physics journal, peer-reviewed, equations checked, written by credentialed scientists, and buried inside its careful technical language was a phrase that had lived for 60 years only in science fiction. A warp drive, not a story, not a fantasy, a design on paper in the actual mathematics of real physics. Within days, the headlines circled the planet. Some called it the breakthrough that would finally carry us to the stars. Others called it hype, dressed up in equations and leading nowhere. Both could not be true, and the answer sitting underneath those headlines is stranger and far more important than either side was willing to admit. Let's start with the dream itself, because it is older than any of us. For as long as we have looked up, we have wanted to go, not to the moon. We have already stood there. Not to Mars. We are still trying. To the stars. To cross the unimaginable gulfs between suns and stand somewhere so far away that the light of home barely reaches it, and to do it inside a single human life. To leave Earth while you are young and arrive somewhere new while you're still alive to see it. That is the dream. And to understand why it has stayed only a dream, we have to be very precise about what we are actually asking. Let's start with the real question, because the question hides a trap. When most people imagine traveling faster than light, they imagine speed, a stronger engine, a bigger rocket, more power, more thrust, more fire. But the real question was never about going fast. It is about whether anything at all, a ship, a person, a single flicker of information, can truly move faster than light itself moves. Not almost, not nearly, faster than the fastest thing the universe has ever permitted. That is the barrier, and everything we are about to follow depends on whether it can be broken. To feel the true size of this problem, look at the closest target we have. Our nearest neighboring star is called Proxima Centauri, a dim red dwarf, a small, cool, faintly glowing sun, tucked into the southern constellation Centaurus. Out of the hundreds of billions of stars in our galaxy, it is the single closest one to us, and it sits about 4.24 light-years away. A light-year sounds like a measure of time, but it isn't. It measures distance. The distance light covers in one full year, moving at its absolute maximum speed. Translated into something we use, Proxima is roughly 25 trillion miles away, about 40 trillion kilometers. Those numbers are so large they stop meaning anything at all, so let me make it real. If you climbed into a car tonight and drove at highway speed, no stops, no sleep, no end, you would not arrive in 100 years. You would not arrive in 100,000. You would still be driving in the same direction after roughly 47 million years. That is the distance to the nearest star, the closest one in the entire sky, and light crosses it in just over 4 years. Light, the fastest thing that exists, needs 4 years and roughly 3 months to make that single trip, because light moves at about 300,000 kilometers every second, 186,000 miles every second. In the time it takes you to say the word second out loud, a beam of light could wrap itself around the entire Earth about 7.5 times. Nothing we have ever measured has gone faster. Not one particle, not one signal. This is the speed limit built into reality itself, and even at that speed, the nearest star is more than 4 years away. So the question turns brutally simple. If light itself takes years to get there, what hope does anything we could ever build truly have? Let's look at the fastest thing we have ever actually launched into the dark. In 1977, NASA sent up a spacecraft called Voyager 1. It flew past Jupiter, past Saturn, and then simply kept going outward into the black. Right now, it holds the record as the most distant human-made object in existence. Nearly 50 years into its journey, it is more than 170 times farther from the Sun than the Earth is. The Earth orbits about 93 million miles out from the Sun, 150 million kilometers. Now take that entire distance and stack it end to end, more than 170 times over. That is how far this small probe has traveled. It moves at about 38,000 miles an hour, 61,000 kilometers an hour, fast enough to cross the entire United States, coast to coast, in under 5 minutes. It is the fastest object our species has ever flung off this planet, and here is what all that speed has actually bought us. This coming November, in 2026, Voyager will cross a threshold no human object has ever reached. It will be one full light day from Earth, about 16 billion miles out, roughly 26 billion kilometers. That means a radio signal, traveling at the speed of light, will now need a full 24 hours just to reach it. Picture an engineer on a Monday morning sending the simple words, "Good morning," out toward the spacecraft. The reply will not come back until Wednesday. 2 full days for light itself to make the round trip after nearly half a century of flight. Now hold that in your mind and remember where Voyager is actually heading. At its speed, crossing the distance to Proxima Centauri would take about 73,000 years. 73,000. All of recorded human history, every empire, every war, every word ever written down, covers only about 5,000. Stack the whole of it end to end, and it fits inside that journey more than 14 times. 73,000 years ago, our own ancestors were just beginning their first great migration out of Africa, spreading across an empty planet they still shared with the Neanderthals. If Voyager had launched toward the nearest star back then, at the dawn of the modern human story, it would only be arriving right about now. That is how long our fastest machine would need, and Voyager isn't even pointed at Proxima. Let that land. Break it down even further. A single light year, just one, would take Voyager roughly 18,000 years to cross. 18,000 years ago, the last ice age still gripped the planet, and not one human being had yet planted a single seed of agriculture. That entire span, the whole climb from ice age hunters to everything we are today, that buys you 1 light year, and the nearest star is more than 4 of them away, and Proxima is the close one. Sirius, the brightest star in our night sky, sits about 8.5 light years away, more than 150,000 years at Voyager's pace, twice the span back to those first African ancestors. Betelgeuse, the red giant burning in the shoulder of Orion, lies hundreds of light years beyond even that, so impossibly far that our fastest machine would need millions of years just to close the gap. These are not distances the human brain ever evolved to hold. We were built to judge the width of a river, the reach of a single day's walk. The space between stars is something our minds can calculate, but never truly feel. And this is the quiet, uncomfortable truth sitting beneath the entire dream. With the only engines we have ever built, rockets, the single technology that has ever carried us off this world, the stars are not merely far away. They sit tens of thousands of years out, sealed behind a wall of pure distance. To reach them inside a single human life, ordinary speed will never be enough. Going faster is not a luxury. It is the only way out, the only door. And whoever finds the key to that door does not simply win a prize. They rewrite the entire future of our species, turning humanity from a single fragile world into something that could one day live scattered among the stars. The whole of our future waits on the far side of it. But physics had bolted that door shut. For most of the last century, that was simply where the conversation ended. The light barrier was absolute. The stars stayed locked behind it, and that was that. The only escape anyone could even imagine carried a name borrowed straight from fiction: the warp drive. The idea that instead of racing through space, you might somehow bend or fold space itself and let it do the carrying, cross light years in years, rather than in tens of thousands of them. For a long time, that was pure storytelling and nothing more. Then, in 1994, a physicist showed it might not be. He wrote down a genuine solution, sitting inside the real equations of Einstein's physics, describing exactly how space might be warped to carry a ship faster than light. The mathematics held up, but the design demanded an ingredient that, as far as anyone could tell, was impossible to build. And so, for the next 30 years, the warp drive lived in a strange kind of limbo. Mathematically possible, practically hopeless. A door that existed on paper with no key that could ever turn the lock. For 30 years, nothing about that changed. And then something did. In 2024, a paper appeared in a respected peer-reviewed physics journal called Classical and Quantum Gravity. It came from a small team of credentialed physicists working with a private research group called Applied Physics, based in Manhattan, alongside scientists at the University of Alabama in Huntsville. And it made a claim that stopped researchers cold. They said they had found a design for what they called a physical warp drive, one that, unlike every version that came before it, did not require the impossible ingredient that had kept the whole idea hopeless for 3 decades. The reactions split the room in two. Some called it a genuine breakthrough, the first real crack in a wall that had stood unbroken for a century. Others called it something colder: clever mathematics, dressed up to look like a doorway, leading somewhere no human being could ever actually go. And here is the contradiction that makes this so difficult to hold. Both sides were staring at the exact same paper, the same equations, the same peer review. One side saw a key, the other saw a trick. They cannot both be right. So let's be honest about what we genuinely know. The paper is real. It passed peer review in a serious journal. Real scientists wrote it, using the authentic machinery of Einstein's physics. Not a press release, not a fantasy, not a hoax. Something real did happen in 2024. A barrier that had not moved in 30 years moved. But moved how far? That is the question hiding inside every single headline. Because a breakthrough is not the same sentence as "they cracked faster than light travel," and the entire space between those two statements is where this whole story lives. If you felt that gap just now, the difference between something changing and something being solved, then you are already thinking exactly the way the physicists are thinking. That instinct is the right one. Hold on to it tightly, because we are going to need it. Because before we can judge what those scientists actually found, before we can know whether that door is truly swinging open or only appearing to, we have to understand the wall itself, not as a number glowing on a screen, but as something woven into the deepest structure of reality. We have to understand why the universe says no, why the speed of light isn't just a limit we haven't beaten yet, but one that physics insists can never be beaten at all. Because the sheer strength of that wall is the only thing that can tell us how extraordinary it would truly be if someone somehow found a way through it. And the closer you look at that wall, the stranger it becomes. It is not a barrier standing somewhere out in space, waiting to be outrun. It is threaded into time itself, into cause and effect, into the very reason the past stays behind us and the future stays ahead. push against it carelessly, and you don't simply travel faster. You begin to unravel the order of events itself. That is what we have to face before anything else. Not the loophole, not the claim, the wall. So let's go looking for a way through that wall, because when you first stand in front of it, it doesn't look like a law of nature. It looks like an engineering problem, a question of fuel and power and ambition. And those are exactly the kinds of problems humans have spent their entire history solving. So maybe the stars are no different. Maybe we simply need a bigger engine, a better machine, more fire. Before we can ever believe this wall is truly unbreakable, we have to be certain it isn't just waiting for the right technology. So we are going to take every serious engine humanity has ever imagined, every real idea for crossing that impossible distance, and test each one against the wall, and watch very carefully what happens to each. Every rocket ever built, from the first firework to the machines that carried people to the moon, obeys one brutal principle. To go forward, you throw mass backward. You carry fuel, you burn it, and you hurl it out behind you, and the push of that exhaust drives you ahead. Simple. But buried inside that simple idea is a trap that has haunted spaceflight from the very beginning, because the fuel itself has weight. And if you want to carry more fuel, you need even more fuel just to push the fuel you're already carrying, and then more still to push that. The demand feeds on itself. A Russian school teacher named Konstantin Tsiolkovsky worked out the mathematics of this more than 100 years ago, and the equation that now carries his name delivers a merciless verdict. The cost of going faster does not rise in a straight line. It rises exponentially. Double the speed you are aiming for, and you don't double the fuel, you multiply it many times over. Push a little harder, and the fuel you need doesn't creep upward. It erupts. Let me make this real. Consider the most powerful machine humanity has ever successfully flown. The Saturn V, the rocket that carried astronauts to the moon. Fully fueled, it weighed close to 3,000 tons, and almost all of that, around 90% of the entire machine, was nothing but fuel. The first stage alone burned through roughly 2,000 tons of it in about 2.5 minutes. 2,000 tons gone in less time than it takes to boil a kettle. Every single second, it devoured about 13 tons of fuel, the weight of 2 adult elephants, vanishing into fire every second for 150 seconds. And all of that fury, that entire ocean of fuel, did one thing. It lifted a small capsule off the Earth and pointed it at the moon. Now hold that in your mind, because here is where it turns frightening. The moon, on average, sits about 384,000 kilometers away, 239,000 miles, close enough that its light reaches your eye in a little over a single second. Proxima Centauri, the nearest star, is roughly 100 million times farther than that. Not 100 times, not 1,000, 100 million. To send a chemical rocket, the only kind we have ever truly mastered, across that gulf, you would need more fuel than exists on the entire planet. Not more than we could afford, more than the Earth physically holds. So the chemical rocket dies at the starting line. But that was never our best idea. Let's look at something far more violent. In the late 1950s, a team of brilliant physicists at a company called General Atomics, among them Ted Taylor and the legendary Freeman Dyson, asked a disturbing question. A single nuclear explosion releases unimaginable energy. What if you could ride it? Their design, called Project Orion, was almost monstrous in its simplicity. You build a massive metal plate on the back of your ship, and then, behind that plate, you detonate nuclear bombs, one after another after another. Each blast slams into the plate and kicks the ship forward, a controlled apocalypse, hammering you toward the stars. And here is the unsettling part. It would actually work. The numbers held up. A nuclear pulse ship could, in theory, reach a few percent of the speed of light, staggeringly faster than any rocket, fast enough to make the crossing to the nearest star in a bit more than a century. But sit with that figure for a moment. More than 100 years. The crew that boarded would never see the destination, neither would their children. Their grandchildren perhaps might arrive, strangers born in the dark between stars, carrying the bones of the people who launched them. We got closer, but the wall didn't move. It only changed who would die before reaching it. So we reach for the engine that powers the stars themselves. Fusion, the process that makes the sun shine, crushing hydrogen together so violently that it floods out torrents of energy. A fusion-powered starship, sketched out by engineers in studies with names like Daedalus, could in principle fly faster still. But here we strike a wall of a completely different kind. We have never managed to control fusion, not in a starship, not even in a stationary power plant bolted to the ground here on Earth. For more than half a century, the brightest minds in physics have been trying to light that fire inside a box and hold it steady. They still cannot, at least not in a way that releases more energy than it swallows, for any length of time that matters. We are trying to ride a star we cannot yet even turn on. Then comes the most extreme fuel the universe allows, antimatter. For every ordinary particle, the universe permits a mirror image twin with the opposite charge. And when the two touch, they do not merely react, they annihilate. Both vanish completely, their entire mass converted into a flash of pure energy, the single most concentrated release of power known to physics. A fuel like that could, in principle, drive a ship to a real fraction of light speed. But now the problem becomes almost cruel. We can barely make the stuff. In the entire history of human civilization, across every laboratory on Earth combined, we have produced less than 10 billionths of a single gram of antimatter, an amount so vanishingly small that, annihilated all at once, it would barely power a household light bulb for a few hours. And even if we could make more, we have nowhere to put it. The instant antimatter touches anything made of ordinary matter, a wall, a tank, a stray speck of dust, it detonates. We would be building a fuel tank for something that destroys whatever it touches. Each idea carries us closer. Each one dies a different death. So we try the opposite of everything that came before. Instead of carrying fuel at all, what if we carry none and let something push us from the outside? Light itself carries a tiny push, a gentle, ceaseless pressure, far too faint for you to ever feel, but absolutely real. Spread a vast, mirror-thin sail across space, and that delicate push can build and build with no fuel to haul along at all. In 2016, a project called Breakthrough Starshot, backed by the investor Yuri Milner and the late Stephen Hawking, proposed the boldest version of this idea ever attempted. Not a giant ship, a chip, a tiny probe weighing about a single gram, roughly the weight of a paperclip, trailing a sail just a few feet across, blasted by a ground-based array of lasers, powerful enough to drive it to 20% of the speed of light. At 1/5 of light itself, it could reach the nearest star in only about 20 years. Within a human lifetime. For the first time, a real plan to touch another star inside a single life. But read the fine print, because it is brutal. That plan works only for something the size of a postage stamp. To push an actual ship, with people, air, water, and walls, to that same speed, you would need a laser drawing more power than all of human civilization currently generates. And even then, at 20% of light speed, our little chip does not stop when it arrives. It can't. It simply screams past the star in a matter of hours and vanishes back into the black, snapping a handful of photographs as it flies by. We did not build a way to travel to the stars. We built a way to glance at one once on the way past. And this is the pattern that should be sinking in now. Chemical rockets, not enough fuel on the planet. Nuclear bombs, a lifetime too slow. Fusion, an engine we cannot switch on. Antimatter, a fuel we cannot hold. Light sails, a postcard, not a voyage. Every idea reaches further than the last. Every idea hits the same wall. Closer, closer, nothing. And that is the moment the real horror arrives. Because every one of those failures looks at first like a problem of engineering. Not enough fuel, not enough power, not enough control. But it isn't. Underneath all of them sits a single, deeper barrier that no engine, of any kind, in any imaginable future, can ever overcome. In 1905, a young patent clerk in Bern, Switzerland, working on physics in his spare hours, quietly rewrote our understanding of space and time. His name was Albert Einstein, and his theory of special relativity revealed something nobody had seen. As an object moves faster and faster, climbing toward the speed of light, the universe begins to resist. Every push you give it does less than the push before. It behaves as though it is growing heavier, harder and harder to accelerate, the closer it creeps toward that limit. Push an object to 99.9% of the speed of light, and it fights back as though its mass had swollen more than 22 times over. And to cross the line completely, to actually reach the speed of light, the energy required does not become very large. It becomes infinite, not enormous, not unimaginable. Infinite. No fuel, no reactor, no engine the size of a galaxy could ever supply it. Think about what that truly means. The wall was never in the rocket. It was never about the fuel we lacked or the engine we hadn't built yet. The barrier is woven into the structure of space and time itself, the geometry of reality. It does not matter how clever the machine is, because the machine was never the problem. You cannot out-engineer the shape of the universe. And here is what almost no one realizes about the speed of light. The limit was never really about light at all. That same speed, 300,000 kilometers every second, 186,000 miles every second, is the speed of cause and effect itself, the absolute maximum rate at which anything in the universe is allowed to influence anything else, the speed at which one moment is permitted to reach the next. Light just happens to travel at it. Break that limit, and you are not merely moving quickly. You are tearing at the thread that keeps every cause ahead of its effect, the very order that keeps the past behind us and the future in front. And every experiment we have ever run agrees. In the great particle accelerators, machines like the one at CERN, buried beneath the border of France and Switzerland, physicists drive tiny particles to more than 99.9% of the speed of light, pouring in colossal amounts of energy. The particles grow heavier, harder to push, exactly as Einstein predicted a century ago. And they never, ever cross the line. Not once in many millions of attempts. The barrier holds, every single time. So if you have been waiting through all of this for the loophole, the secret engine, the clever trick, the better machine that finally smashes through, here is the hard truth. By going faster, it does not exist. Most physicists regard the speed of light not as a challenge to be beaten one day, but as one of the most absolute laws in all of science. The door we have been searching for does not open by pushing harder. And yet, if that lands as a disappointment, if some part of you quietly refuses to accept that the stars are simply forbidden to us, then hold on to that feeling, because it turns out you are asking exactly the right question, just not in the way you think, because Einstein's law is far more precise and far stranger than it first appears. It forbids anything from moving through space faster than light. It says nothing at all, about how fast space itself is allowed to move. And space, it turns out, is not the empty, fixed, motionless backdrop we picture. Space is not a stage that simply holds the actors. Space can stretch. Space can bend. Space can move. And before this is over, we will see that space has already been caught moving faster than light, out there in the depths of the cosmos right now, breaking no law at all. If space itself can move, carrying everything inside it along for the ride, then the wall we just called unbreakable might have a hidden door in it after all, one that opens without shattering a single rule. And the idea that cracked it open did not come from a space agency. It did not come from a weapons lab or a billion-dollar program or any of the places you would expect. It came from a single physicist chasing something most of his colleagues dismissed as a childish fantasy borrowed from television, and daring to treat it instead as serious physics. What he wrote down would sit on the shelf, ignored and declared impossible for 30 years, until a small private laboratory decided to pick it back up, and that is where everything changes. The year was 1994. The physicist was Miguel Alcubierre, a young Mexican theorist who loved Star Trek and decided, almost as a private game, to ask whether the warp drive from the show could be written down in the real language of physics. What he found was not a fantasy. He discovered that on paper, you do not have to break the speed of light to cross space quickly. You only have to stop trying to move through space, and instead move space itself. The mathematics held. The solution was genuinely real, but buried inside it sat a single poisonous requirement that would condemn the whole idea to 30 years of silence, until, decades later, a small private laboratory in Manhattan refused to accept that the door was closed. So picture what he was proposing. Instead of building a faster ship, you build a bubble, a pocket of perfectly flat ordinary space, with your ship resting calmly inside it. Then you reshape the space around that bubble. You contract it in front of you, squeezing the distance ahead shorter, and you expand it behind you, stretching the distance you have already crossed longer. The bubble, with you inside it, gets carried forward on that wave of warping space, the way a surfer is carried by a swell that is itself moving. You never move through your local space at all. You sit perfectly still, and the universe rearranges itself around you. And here is the beautiful part. This was not hand-waving. When Alcubierre wrote it down as a precise solution to Einstein's equations, the same equations that govern gravity and stars and the bending of starlight, tested for over a century, it worked. The geometry was valid. By the rules of general relativity, such a bubble could, in principle, exist, and it could carry you faster than light without you ever locally breaking the speed limit, because that limit only forbids moving through space, and you, inside your calm bubble, are not moving through space at all. But then came the catch, and it was a brutal one. To bend space into that exact shape, Alcubierre's equations demanded a very particular kind of material, not ordinary matter. They required exotic matter, a substance with negative energy, negative mass, stuff that, instead of pulling things toward it like every object you have ever held, would push them away. Matter that falls upward. And in all of human science, across every experiment ever performed, no one has ever found such a thing. It may not exist at all. So Alcubierre's warp drive was real and impossible in the very same breath. A perfect blueprint for a machine that needed an ingredient the universe might simply not contain. For 30 years, that is where it stayed. Mathematically possible, physically hopeless. A door drawn flawlessly on the wall, with no key that could ever fit the lock. Then a small group of people decided that hopeless was not the same word as proven impossible. Let me tell you about applied physics. A private research outfit, headquartered at 477 Madison Avenue in Manhattan, founded by a man named Gianni Martira, not a tenured academic, but a self-taught physicist and technology entrepreneur, carrying an unusual conviction. He believed the warp drive deserved to be treated not as science fiction, but as an engineering problem, a puzzle to be solved, not a fantasy to be enjoyed. and he gathered a small team of credentialed physicists to do exactly that, to publish real work in real peer-reviewed journals under the cold scrutiny of other scientists. Their first major strike landed in 2021. Alexei Bobrik, an astrophysicist, together with Martyr, published a paper in the journal Classical and Quantum Gravity with a quietly radical title, Introducing Physical Warp Drives. And what they built was a unifying framework, a single picture that could describe every possible warp drive at once. In that picture, a warp drive has three regions: far on the outside, ordinary flat space, undisturbed; deep on the inside, a second pocket of perfectly flat space, the passenger area, where you would sit feeling completely normal, completely untouched; and between the two, a shell, a wall of warping space-time that does all the work, all the bending, all the carrying. And inside that framework, they proved something that cut two ways at once. They showed that any warp drive, every version of it, no matter how exotic, is, at its heart, simply a shell of matter. And like any shell of matter, like any ordinary object, it cannot just accelerate itself past the speed of light for free. It needs something to push it. That single result quietly killed the fantasy of effortless, faster-than-light flight. But in the same stroke, it dragged the subliminal warp drive, the slower-than-light version, out of fiction and into the realm of buildable physics. And then they did something concrete. By reshaping the bubble, they slashed the amount of negative energy Alcubierre's design had demanded, not by a little, but by roughly 100-fold. The impossible mountain of exotic matter suddenly looked a great deal smaller. For the first time in 30 years, a fully physical warp drive, one that might need no impossible ingredient at all, began to look like something a person could actually chase. The conversation had shifted. Warp drive was no longer forbidden by physics. It was becoming an engineering problem we don't yet know how to solve. And those are very, very different sentences. But the real shock was still 3 years away. In 2024, on the 29th of April, a landmark paper appeared, again in Classical and Quantum Gravity, led by a physicist named Jared Fuchs, working with the applied physics team and collaborators at the University of Alabama in Huntsville and Israel's Technion. Its title was modest: Constant Velocity Physical Warp Drive Solution. Its claim was anything but. They said they had found a warp drive that satisfied all of the energy conditions. Now, let me explain what that means, because it is the whole point. The energy conditions are the basic rules that ordinary, well-behaved matter always obeys. There are 4 of them, with names like the weak, the null, the dominant, and the strong condition. Strip away the technical language, and together they say something simple. Real matter has positive energy. Energy does not flow faster than light, and gravity pulls rather than pushes. Every sane substance in the universe follows these rules. Alcubierre's drive shattered them. This one, they claimed, did not break a single one. All 4 satisfied at once. No negative energy, no exotic matter, none. How? Not by expanding and contracting space as the old picture imagined. The lead author described it differently. Picture a vast amount of energy, ordinary, positive energy, circulating rapidly around the passenger cabin, around and around, like a smoke ring hanging in the air. On the inside of that ring, the swirling energy drags space-time into a kind of conveyor belt, carrying the passengers along by gravity alone. A shell of normal matter on the outside, a current of flowing space on the inside, and a calm, untouched cabin riding in the middle. And they did not just claim it, they built it inside a computer using their own software, an open-source toolkit they called Warp Factory, written so that any physicist on Earth could download it and check their work line by line. The program takes a proposed warp design and tests every single point inside it against the laws of physical matter. where the matter is physical, allowed, sane, it colors that point blue. Where it violates the rules, where it demands the impossible, it colors the point red. For 30 years, every warp drive anyone had ever tested bled red, and when they ran this one, the screen filled with blue, point after point after point, physical, allowed, real. A door that had been bolted shut for 3 decades had, on a computer screen, quietly turned blue. Sit with how strange that is. Not a press release, not a hope, a specific numerical solution, published, peer-reviewed and downloadable by anyone, describing a warp drive that the known laws of physics do not forbid. And then comes the caveat, buried beneath all the celebration, the line you have to read very carefully, because most of the headlines did not. The solution is strictly subluminal, slower than light. No broken barrier here, no Star Trek leap across the galaxy in an afternoon. The drive that turned the screen blue cannot, by its own design, exceed the speed of light. The wall from before still stands, exactly where it stood. And yet, even slower than light, this thing would do something close to miraculous. Because the passenger sits in perfectly flat space, the passenger feels nothing. No G-forces, none at all. In a rocket, hard acceleration crushes you. Into your seat, push too hard, and it kills you. Inside a warp bubble, you could accelerate as violently as you liked and feel not the faintest tug because you are not truly accelerating. The space around you is doing the moving, and that single fact changes everything about distance. In principle, if such a craft could ever be built and powered, it could climb to a large fraction of the speed of light without harming a soul aboard, turning a journey to Mars into a matter of days, turning the crossing to the nearest star from tens of thousands of years into something closer to years or decades. Not forbidden anymore, just unbuilt. Because make no mistake, this is not a free ride. The energy such a drive would demand is still staggering, far beyond anything humanity can currently generate. The materials it would require may be impossible to make, and not one piece of the hardware has ever been built, or tested, or shown to work outside a simulation. A blueprint glowing blue on a screen is a profound thing, but it is not a ship. And still, the work kept moving. In 2025, it took a turn that felt almost uncanny. Harold White, an aerospace engineer who, years earlier, had been the first and only scientist to study warp drives for NASA, published a new design with his team at a company called Casimir. Instead of one smooth, continuous bubble, White broke the warping region into discrete cylindrical channels, pods, each one a tunable little engine of curved space arranged around the ship, with a calm, flat, habitable region sitting protected in the middle, where a crew could actually live, and the shape those pods formed carried an unmistakable resemblance to something millions of people had seen before, the twin-engine nacelles slung beneath the Starship Enterprise. White himself said the likeness was not merely cosmetic, that science fiction's old guess at what a warp ship should look like might be brushing up against what the physics genuinely requires. But honesty matters here. White's elegant pods did not escape the original curse. His design still tucks exotic matter, that same negative energy, into those cylindrical channels. It makes the bubble look buildable. It makes the interior livable. But it does not solve the problem that the positive energy solution claimed to solve. 2 different roads up the same mountain, both still unfinished. And here, the story does something important. It refuses to settle, because an extraordinary claim invites extraordinary scrutiny, and the scrutiny came hard. Even before any of this, back in 2022, 3 physicists, Jessica Santiago, Sebastian Schuster, and Matt Visser, had proven a sweeping result. Generic warp drives, the broad family of them, still violate one of those sacred rules of sane matter. the null energy condition, and in 2026, a wave of fresh reassessments arrived. A team in France, Hamed Barzagar, Thomas Buchert, and Quentin Vigneron, argued that when you apply Einstein's general relativity rigorously, most claims about these physical warp drives have to be reassessed. They even proved new no-go theorems, formal mathematical proofs that certain doors cannot be opened at all, and their deepest objection cuts right to the bone of the method. You can, they point out, draw any shape of space-time you wish, and then run Einstein's equations backward to calculate exactly what matter would be needed to produce it. But the matter that comes out the far end may be nonsense, a fantastic substance that corresponds to nothing real. Whether a warp drive truly obeys the energy conditions, they argue, can depend on who is looking at it, on the observer, the frame, the angle of view. And another 2026 analysis by the physicist Anne Thiele found that when you check these designs with enough care, small but genuine violations begin creeping back in. And then comes José Natario, one of the very physicists whose own work helped shape this entire field. This year, he said it plainly, faster-than-light travel, in his view, remains impossible, and he pointed at two problems almost no one likes to discuss. Even if you could somehow build the bubble, no one knows how to steer it, and no one knows how to make it stop. So which is it? A genuine historic milestone, the moment warp drives stopped being forbidden and became merely monstrously difficult, or a gorgeous piece of mathematics that dissolves the instant you ask what it is truly made of, and how you would ever turn it or halt it? The honest answer, right now, tonight, is that no one yet knows. The argument is alive. The evidence is still being weighed. But notice the one thing that haunts every single version of this story. Alcubierre's original, the positive energy shell, White's starship pods, even the critics' sharpest counter-arguments. The same ghost keeps drifting back through all of them. The same impossible ingredient that poisoned the very first design in 1994. Negative energy, exotic matter. That ingredient is the hinge on which this entire dream swings, and so far we have been treating it as a single line in the story, a catch, a footnote. But to understand whether that door is genuinely opening or only seeming to, we have to go all the way back to the beginning, back to that young man and his television-born idea, and the strange, beautiful loophole he actually found. Because the loophole is far stranger than a footnote, and it started everything. So, let me take you back 30 years to 1994, to a young graduate student at the University of Wales in Cardiff named Miguel Alcubierre. He was finishing a PhD in the mathematics of black holes, the kind of work that fills chalkboards with equations almost no one outside the field can read. And like millions of people, in his off hours, he watched Star Trek. He watched starships cross the galaxy in the time it takes to finish a conversation, casually outrunning light itself. And where most fans simply enjoyed it, Alcubierre did something different. He looked at that fictional warp drive, and he asked with complete seriousness whether the real universe might allow it. In his own words, he was watching the show and thought there must be a way to do this properly. So he sat down and treated it like a homework problem. And inside Einstein's own equations, he found a loophole, a way the universe already breaks its own speed limit, quietly, constantly, every single day. Here is the crack he found. Remember the iron law from before. Nothing can move through space faster than light, but Alcubierre fixed on the exact wording of that law because it contains a gap. The rule limits how fast things can move through space. It says absolutely nothing about how fast space itself is allowed to move. And that is not a clever word game. It is something we can actually see, written across the night sky. Space is not a fixed, frozen stage that the universe is painted onto. Space stretches. It has been expanding ever since the beginning of time. a discovery Edwin Hubble made nearly 100 years ago, watching distant galaxies drift away from us. And here is the part that breaks the mind a little. The most distant galaxies we can see are receding from us faster than light. Not because they are racing through space at superluminal speed, they are not, but because the space between us and them is growing, everywhere, all at once. Stretch enough space between 2 points, and the gap can widen faster than light can cross it, and no law is broken, because nothing is moving through space at all. The space is simply getting bigger. Picture dots drawn on a vast elastic sheet. The dots never crawl across the surface. They sit perfectly still, yet stretch the sheet and the dots rush apart, and 2 dots far enough apart can separate faster than any runner could ever travel between them. The motion isn't in the sheet. The motion is the sheet. That was the loophole. And Alcubierre asked the obvious next question. If space itself can carry distant galaxies apart faster than light, could you make space carry a ship the same way? Deliberately? On purpose? So, he designed it. Picture a bubble of perfectly flat, ordinary space-time, with a ship resting quietly inside. Then just outside that bubble, you do to space exactly what the universe does on a cosmic scale, but under control. You contract space in front of the ship, pulling the destination closer. You expand space behind it, pushing the origin away. The bubble, with the ship inside, gets swept forward on that wave of warping space. And the most beautiful detail of all, the crew inside feels nothing. No crushing force, no acceleration pressing them into their seats. Alcubierre showed that they would ride in free fall, in calm, flat space, even as the bubble itself tore across the cosmos. They would sit still, and the universe would do the moving. But now we come to the deeper question. How do you actually write such a thing down? How do you prove it is real, and not just a nice picture? The answer lives in a single word, a metric. And this is worth slowing down for, because everything hinges on it. A metric is, quite simply, a recipe. A set of instructions that tells you how distance and time behave at every single point in a region of space-time. How far apart things really are. How fast clocks really tick. Flat, empty space has a metric, worked out by a mathematician named Hermann Minkowski. The warped space around a black hole has its own metric, derived by Karl Schwarzschild in 1916. Remarkably, while he was serving in the trenches of the First World War, a spinning black hole has another, found by Roy Kerr decades later. Each metric is a different valid solution to Einstein's equations, a different possible shape that reality is allowed to take. And here is the move that made Alcubierre famous, and, much later, controversial. Normally, you start with the matter, a star, a planet, and you calculate the shape of space it creates. Alcubierre ran it backward. He started by writing down the shape he wanted, the warp bubble, and then ran Einstein's equations in reverse to ask what kind of matter would be required to produce it. He drew the destination first. Then he solved for the road. In May of 1994, he published the result in the journal Classical and Quantum Gravity. The title was almost absurdly plain: The Warp Drive, Hyper-Fast Travel Within General Relativity. It was short, only a handful of pages, and it became one of the most cited, most discussed ideas in all of modern theoretical physics. Because the mathematics was airtight, it was a genuine, exact solution. By the rules of general relativity, the warp bubble could exist, and then the reverse calculation handed back its answer, and the answer was a nightmare. To bend space into that exact shape, Alcubierre's equations demanded a kind of matter that has never been seen. Not rare matter, not expensive matter, impossible matter, with negative energy, negative mass. Let me make you feel what that means, because the words slide by too easily. Ordinary matter pulls, every speck of it, always toward you. This stuff would do the reverse. It would push you away. It would fall upward. It would repel. Anti-gravity. Take a stone and drop it, and it falls. Drop a stone made of negative mass, and it would rise. Set it on the table beside you, and instead of its gravity tugging you gently closer, it would shove you away. Nothing in all of human experience behaves like this. Not one object you have ever held, thrown, or watched fall. No laboratory has ever isolated a single gram of it, and to this day, no one knows for certain whether it exists anywhere in the universe at all. So, Alcubierre's warp drive was, from its very first day, two contradictory things at once. A perfect, valid, mathematically flawless blueprint for a machine that required a fuel reality might simply refuse to provide. And then came the numbers, and the numbers were where the dream seemed to die. Alcubierre ran the estimate for a bubble large enough to wrap around a ship roughly 200 meters across, about 650 feet, a little under the length of 2 football fields laid end to end, and the amount of negative energy it would take, by his own calculation, an amount comparable to, and by some later estimates greater than, the mass of the entire observable universe. Sit with that for a moment. Every star, every planet, every galaxy in all of creation, hundreds of billions of them, the total mass of everything we can see. You would need that much, and then conjure it in a form of matter that does not exist, just to move a single ship. Then, in 1997, 2 physicists drove the final nail. Michael Fenning and Larry Ford at Tufts University took Alcubierre's design and applied the harsh rules of quantum field theory, specifically a set of limits called the quantum inequalities, which restrict how much negative energy can exist in one place, and for how long. They titled their paper, Without Mercy, The Unphysical Nature of Warp Drive. What they found made it worse than anyone had imagined. To hold the bubble together, its wall, the warping shell itself, could be no thicker than a few hundred times the Planck length, and the Planck length is the smallest distance that has any meaning in physics at all. A single proton, already so small that millions would fit across the width of a human hair, is about 100 billion times larger than the Planck length, so the design demanded that you take the impossible energy of an entire universe and crush it into a shell vastly thinner than the particles inside an atom. Their conclusion was simple and damning, physically unattainable. The figures were so monstrous, so far beyond absurd, that many physicists simply assumed there had to be a mistake hiding somewhere in the math. There wasn't. The loophole was real. Alcubierre had genuinely found a door in the wall, a true mathematically valid way to cross space faster than light without ever breaking Einstein's law. But the door had a lock, and the only key that could open it was forged from a metal that might not exist anywhere in the cosmos. And this is exactly where the story should have ended. A breathtaking solution with no possible path to a real machine, a flawless blueprint for the impossible, a beautiful, perfect, useless dead end, admired, cited, and quietly shelved. But it did not end there, because that number, that universe-sized mountain of negative energy, turned out not to be fixed. It was about to start falling, not all at once, not in a single triumphant breakthrough, but slowly, stubbornly, one paper at a time. A quiet line of physicists would take Alcubierre's impossible figure and begin chipping it down from the mass of the entire universe to something smaller, and then smaller still. And here is what makes that descent so quietly thrilling and so important. Somewhere along that falling curve, if the number could be pushed low enough, the warp drive would cross an invisible threshold. It would pass from forbidden by the sheer size of the cosmos to merely, monstrously difficult, from a fantasy that violates the universe to an engineering problem that just awaits a solution. No one knew exactly where that line was. No one knew if the number would ever fall far enough to reach it. The only way to find out was to follow the figure down and watch how far it could go. So the question that hung over everything was the number, that impossible universe-sized mountain of negative energy. Because as long as it stayed that high, the warp drive remained exactly what the critics had called it, a flawless equation for a machine that reality would never permit. And so, quietly, almost stubbornly, a handful of physicists set out to do the one thing that might save the dream. Not to build the engine, not yet, but to attack the number itself, to take that impossible figure and force it down. What followed was a slow, patient war of attrition, fought across decades, in journals most people will never open. There were no headlines for most of it, no press conferences, just equations refined and re-refined, each one trying to shave a little more off a bill the size of the cosmos. And it began with a strange and beautiful idea that a thing could be far bigger on the inside than it is on the outside. The first real blow landed in 1999, just 5 years after Alcubierre. A physicist named Chris van den Broek, working at the Free University of Brussels, looked hard at the warp bubble and asked a question no one else had thought to ask. Everyone had simply assumed that the bubble's outside and its inside had to be the same size, that a ship-sized interior demanded a ship-sized exterior, wrapped in a ship-sized fortune of negative energy. But van den Broek realized that curved space-time makes no such promise. In the strange geometry of general relativity, you can build a pocket of space whose interior is vast, while its exterior, the part that actually has to be sheathed in that ruinously expensive exotic matter, is almost unimaginably small. Let me try to make that feel real, because it sounds like nonsense, and it isn't. Picture a tiny opening, no wider than the eye of a needle, hanging in the empty dark. You drift up to it, you pass through, and you find yourself standing inside a room the size of a cathedral. From the outside, almost nothing, a speck you could miss entirely. From the inside, an entire world. Your instinct screams that this is impossible, that the inside cannot be bigger than the door. But that instinct was built for a flat world of tables and rooms. In Einstein's universe, where space itself can be stretched and folded, a small surface really can enclose an enormous volume. It is not a trick of the eye, it is the geometry. And that one insight changed the math completely, because the price of a warp drive is paid almost entirely at its surface, the thin shell where space is bent the hardest. So if you could shrink the bubble's exterior, its outer skin, down toward the scale of an atomic nucleus, a thing so small that millions upon millions of them would fit across the width of this sentence, then the bill for the negative energy collapsed right along with it. Van den Broek's design hid a roomy, perfectly flat, ship-sized interior behind an outer shell almost too tiny to picture, and in doing so, he dragged the energy requirement down from the mass of the entire observable universe to something on the order of just a few times the mass of our own sun. Now, be honest with yourself, that is still a catastrophic, ruinous, flatly impossible amount of negative matter. No one is harvesting suns, but pause and feel the size of that drop, from every star and every galaxy in all of creation, down to a small handful of suns. In a single paper, the impossible had become a great deal less infinite, and his design did something else too, something quieter but important. It came close to satisfying one of those sacred rules of well-behaved matter, the weak energy condition, the simple demand that the energy any observer measures should never fall below nothing at all. Alcubierre's original drive had shattered that rule without hesitation. Van den Broek's version still bent it, but it bent it far less violently. The door was still locked, but you could feel the lock beginning to loosen. The chipping continued. In 2002, the Portuguese physicist José Natario, And hold on to that name, because decades later he will return as one of the sharpest skeptics this whole story produces, added a piece of his own. Alcubierre's original bubble worked by expanding and contracting space itself, stretching it open behind the ship and squeezing it shut ahead. Notario proved something subtle and surprising, that you didn't strictly need any of that stretching at all. He built a version of the warp drive where space simply flows around the vessel, sliding past it, smooth and sideways, the way a river slips around a stone without the stone ever having to move. No expansion, no contraction, just a steady current of space, carrying the ship along inside it. Each of these papers, taken on its own, was a small thing. One shaved away a little energy. One repaired a technical flaw. One found a cleaner, more elegant way to bend the geometry. And after all of it, after years of this, the numbers were still impossible. No engineer alive could build any of these machines. But the trajectory, the direction the figure kept moving, pointed unmistakably in one direction, downward. Year after year, paper after paper, the mountain was quietly getting shorter. And then, in 2011, the warp drive gained something it had never had in its entire existence: a government space agency standing behind it, NASA, inside the Johnson Space Center in Houston, in a small and almost obscure outfit called Eagle Works. Formerly, the Advanced Propulsion Physics Laboratory, an engineer named Harold White, known to nearly everyone simply as Sonny, picked up the thread. White was a believer in the careful, credentialed sense of that word, a man with a doctorate in physics who thought the warp drive deserved real hands and real instruments, not just admiration from a distance. And in 2011, at a gathering called the 100-Year Starship Symposium, he presented a piece of work with a deceptively humble title, Warp Field Mechanics 101. White's contribution was, at its heart, an engineer's instinct brought to bear on a physicist's problem. He took the wall of the bubble, that razor-thin, agonizing shell that Fenning and Ford had shown was the source of so much of the cost, and he asked a simple question: what happens if you stop making it a knife edge? What if you let the wall grow thicker, softer, more gradual? And alongside that, he reshaped the bubble itself. Alcubierre had imagined a sphere. White flattened and opened it into a torus, a donut, a thick ring of warped energy encircling a calm, flat, untouched pocket of space in the very middle, where the ship would ride. And when he ran the numbers on that thicker, donut-shaped field, the energy requirement fell yet again. And this time, the figure that came out the other end was genuinely arresting to look at. A commonly cited number from White's work brought the negative energy needed down to roughly 700 kilograms. 700 kilograms. Let me set that beside something you can actually hold in your mind. It is almost exactly the mass of the Voyager 1 spacecraft, that same lonely probe we stood beside at the very beginning of all this, the fastest object our species has ever flung into the dark. White himself reached for that very comparison. The warp drive on paper had gone from demanding the mass of the entire cosmos to demanding the weight of a single space probe small enough to picture sitting in a garage. Now, here is the moment where honesty has to seize the wheel. Hard. That 700 kilograms is not 700 kilograms of ordinary matter. It is 700 kilograms of exotic matter, negative energy, the substance that falls upward, that repels instead of attracts, the impossible material that, to this very day, no human being has ever produced even a single atom of. So the warp drive remained, in the most literal and unforgiving sense, impossible. Not 1 gram of its fuel exists anywhere we can reach. But, and this is the entire reason the long climb down matters, it had become impossible on a completely different scale. The dream had moved from a number that mocked the whole universe to a number you could write on the side of a spacecraft. From cosmic to almost human. And White was not content to stay among the equations. He wanted to touch the thing. Inside Eagle Works, he and a colleague built an instrument they named the White-Jude Warp Field Interferometer, a modification of one of the most famous and sensitive devices in all of physics, the Michelson interferometer, the same elegant design that more than a century ago helped overturn everything we thought we knew about light and space. White's hope was almost audacious in its smallness. He was not trying to fly to another star. He was trying to create a warp in space-time so faint, a distortion of barely 1 part in 10 million, that it might be detected on a tabletop in a quiet laboratory with nothing more than a laser beam. Not a voyage, a flicker, a whisper in the dark, just enough to prove the effect was real. And here the story turns honest and a little sad, because the results never came. The signals White's team went looking for were faint, ambiguous, hovering right down at the level of background noise, never clean, never repeatable, never the unmistakable fingerprint of genuinely warped space. Independent physicists examined the apparatus closely and argued pointedly that the device could never have detected a true space-time distortion in the first place, that any flicker it registered was far more likely to be tiny shifts in air temperature or stray electrical effects between the charged plates than any real bending of reality. And Eagle Works itself had, by that time, attracted heavy skepticism for other reasons entirely, most famously its work on the so-called EM drive, a proposed engine that seemed to produce thrust out of nothing at all, in apparent defiance of the most basic laws of physics, and which later, more rigorous experiments failed to reproduce. So the one laboratory that had carried the warp dream inside the walls of a NASA building became, fairly or not, wrapped in a fog of doubt. And White himself seemed to understand precisely where things stood. He reached for a particular image to describe it. Warp travel, he said, was still waiting for its Chicago pile moment, a reference to 1942, to the very first controlled nuclear chain reaction, a crude little stack of graphite and uranium built beneath the stands of a stadium in Chicago, which produced only about half a watt of power, barely enough to light a small bulb. In raw terms, it achieved almost nothing, but it proved the principle was real, and a few short years later, that same principle had reshaped the entire world. Warp physics, White was quietly admitting, had not yet had even that, not even its half-watt flicker, not yet its first undeniable spark. And yet, step all the way back and look at the full shape of the climb. In less than 2 decades, a small scattered band of physicists had taken the single most impossible number in modern science and marched it down deliberately, step by step, from the mass of the entire observable universe to the mass of a few stars, to the weight of one small spacecraft. The energy budget for bending space had fallen from a cosmic scale all the way down to something you might almost call a motorcycle scale. The shrinking had been real, and it had been astonishing. But every single step of that descent had been paid for in the same forbidden currency: negative energy, exotic matter, the substance that may simply not exist. And so, the whole dream now came to rest on one unavoidable question, the question that all the clever geometry had only been circling without ever daring to face. Forget how much of it you need. We had shrunk that brilliantly against all odds. The real question, the one that would decide whether any of this was ever more than gorgeous mathematics on a page, was simpler and far more frightening than any number. Can negative energy exist at all? Even a trace of it? Even a single fleeting whisper? Because if the answer is yes, if the universe permits even the smallest quantity of that impossible substance, then the door we have been standing before might genuinely open. But if the answer is no, then every elegant solution, every shrinking figure, every beautiful donut-shaped field collapses at once into a dream that was never going to leave the paper it was written on. and the hunt for that answer would carry us somewhere we did not expect to go, out of the warp drive entirely and into a second, stranger doorway that physicists had been quietly studying all along. A tunnel, not around space, straight through it. There has been a quiet assumption running underneath this entire story. Soft, comforting, almost invisible. The assumption that the only thing standing between us and the stars is the building of the thing. That if we could just shrink the number far enough, find the fuel, switch on the engine, then the hard part would be behind us and the rest would be triumph. But that assumption is wrong, because even a perfect warp drive, fully built, fully fueled, humming and ready, hides a set of dangers that are not engineering inconveniences to be solved later. They are uniquely, physically lethal, and every one of them gets worse the faster you go. So let us look carefully at what actually happens when you try to truly outrun light. The first catch is the most quietly terrifying, because it sounds at first like a small inconvenience. When your bubble travels faster than light, its front wall, the leading edge, the part of the warp out ahead of you, is moving faster than light too, and that means something no captain would ever want to hear. Any signal you send forward, a pulse of light, a radio command, anything at all, can never catch up to the front of your own ship. The leading edge outruns the very light you would use to reach it. You are sealed off, causally, from the front of your own bubble. The crew, sitting calmly in the middle, is cut off from the wall that is doing the steering. Sit with what that means. You cannot steer. You cannot adjust your course. You cannot see what is coming, and you could not dodge it even if you could. And worst of all, you cannot stop, because to switch off that front wall, to tell it to slow, you would have to send it a signal, and the signal can never arrive. Alcubierre himself flagged this from the beginning. The traveller at the centre is causally severed from the edge of his own machine. The implication is chilling. To bring the bubble to a halt, something would have to control it from the outside. Some system waiting at the destination, set up in advance, at a place you have not reached yet and cannot signal ahead to. A faster-than-light ship is not really driven at all. You launch it the way you fire a bullet. Aimed once, released, with no driver, no brakes, and no way to turn. A projectile hurled across the cosmos, hoping nothing stands in its path, and that is only where the trouble begins. In 1996, a physicist named Alan Everett at Tufts University took Alcubierre's beautiful metric and made a small, almost casual modification to it, and what fell out was something the universe is not supposed to permit. He showed that warp drives, with just a little adjustment, can be used to build closed time-like curves, paths through space-time that loop back and reconnect with their own past. In plain terms, a true faster-than-light drive, married to Einstein's relativity, becomes a time machine, and the reason is woven into the deepest fabric of relativity itself. Observers moving at different speeds do not agree on what counts as now, on which distant events are happening at the very same moment. For one observer, a faster-than-light signal races forward in time, but for another, moving differently through space, that exact same signal arrives before it was ever sent. Chain two of those jumps together, and you have not merely whispered a message into the past. You could arrive there yourself, and time machines drag behind them the kind of paradoxes that make physicists go pale. Effects arriving before their causes, histories that erase themselves, a universe where the thread of before and after comes untied. Going faster than light, it turned out, did not just threaten the crew, it threatened cause and effect itself, but the deepest horror was hiding in the front wall, because that leading edge, the boundary your own signals can never cross, behaves, in a very precise sense, like the edge of a black hole, a horizon, a one-way surface, a line in space-time that light cannot get past. And in 1974, Stephen Hawking proved something that changed physics forever. that such horizons are not silent and not dark. They glow. Through the strange machinery of quantum mechanics, every horizon is forced to radiate a faint stream of particles, what we now call Hawking radiation. Empty space, it turns out, is never truly empty. Everywhere, in every sliver of the vacuum, pairs of particles are flickering into existence and vanishing again, far too fast to ever be caught. But at the edge of a horizon, that flickering becomes a trap. One partner of the pair slips across the boundary and is swallowed forever, while the other is stranded outside, with nothing left to annihilate against. And so it escapes, real and permanent, glowing off the horizon into the dark. And here is the part that turns the stomach. The smaller the horizon, the hotter it burns. This runs exactly opposite to your instinct. A vast, giant black hole radiates with a cold, almost imperceptible warmth, while a tiny one rages white-hot and furious. And a warp bubble's front wall is not a vast, gentle horizon. It is a sharp, thin, vicious little blade of one. In 2009, 3 physicists, Stefano Finazzi and Stefano Liberati, working at the International Research School SISSA in Trieste, Italy, alongside Carlos Barceló in Spain, sat down and did the calculation properly. Not for some idealized eternal bubble, but for the realistic case, a warp drive switched on out of ordinary flat space and accelerated past the speed of light, and what they found was a death sentence written into the geometry itself. They discovered that superluminal warp bubbles are semi-classically unstable. The Hawking radiation does not simply appear at the front wall and sit there politely. It accumulates. It piles up against the leading edge, and it grows, exponentially, relentlessly, without any upper limit at all. How hot? The temperatures climb toward the single most extreme number in all of physics, the Planck temperature, roughly 10 to the 32 Kelvin. That figure is almost meaningless to say aloud, so let me tell you what it actually is. The Planck temperature is the hottest temperature that physics can even describe. The heat of the universe, a sliver of an instant after the Big Bang, the point at which the known laws themselves break down and stop making sense. There is no hotter beyond it that our physics can speak of, and the front wall of a faster-than-light ship would be racing toward exactly that. Inside a furnace like that, the crew would not be in danger. They would not be injured. They would be erased, vaporized, gone. No hull, no shielding, no material that has ever existed or ever could exist would survive for even an instant. The ship would cook itself to atoms the very moment it crossed the threshold into superluminal speed. The faster-than-light starship, the sleek dream of a century of fiction, would become its own crematorium. And, almost unbelievably, it gets worse, because space is not empty. We imagine the void between the stars as a perfect, sterile nothing. It very nearly is. On average, interstellar space holds only about one atom, usually a single, lonely hydrogen atom, in every cubic centimetre, a volume about the size of a sugar cube. That is a thinness almost beyond imagining. The ordinary air filling the room around you right now is more than 1 billion times denser than that. Space is, for all practical purposes, empty, but, for all practical purposes, is precisely the trap, because the journey between stars is so vast that even one atom per sugar cube of space adds up to an ocean. And in 2012, 3 researchers at the University of Sydney, Brendan McMonagall, Geraint Lewis, and Philip O'Byrne, worked out what happens to all those atoms when a warp bubble ploughs through them. The bubble sweeps them up. It gathers the stray hydrogen, the dust, the lone electrons, even the faint photons left over from the birth of the universe, and it traps them, freezing them against its leading edge, where they pile higher and higher with every light year crossed. Picture a plough driven across 1,000 miles of snow, and never once allowed to shed its load. And then you arrive, and you decelerate, and in that instant, everything the bubble has been hoarding for the entire voyage is released, all at once in a single, focused, forward-facing blast. McMonagall said it plainly: the energy of that burst has no upper limit. The farther you have travelled, the more catastrophic it becomes. Now follow that to its conclusion, because it is genuinely disturbing. That forward beam, the accumulated blue-shifted fury of an entire interstellar crossing, would be unleashed directly ahead of the ship, aimed squarely at wherever you were trying to go. Powerful enough, the Sydney team found to annihilate whatever waits at the destination, to scorch a planet, to sterilize the very world you cross the galaxy to reach. A faster-than-light ship does not simply travel to the stars. It arrives as a weapon, an accidental planet killer, fired ahead of itself, striking its target at the exact moment of arrival. You would obliterate the thing you came to find. So this is the true face of going faster than light. Not a triumphant leap between the stars, but an uncontrollable bomb. Blind, unstoppable, burning itself alive and lethal to everything in front of it. But here, and this matters more than anything else in all of it, look closely at the single thread that runs through every one of these horrors. The runaway horizon, the hawking fire, the instability, the hoarded, deadly harvest, the unravelling of time itself. Every last one of them is born from the same act, the act of going faster than light. And that points us towards something quietly redemptive. Drop below light speed, stay subliminal, and the front wall never becomes a horizon at all. No horizon means no hawking radiation. No radiation means no roasting, no runaway instability, no semi-classical death. The time machine never forms. The paradoxes never open. The dangers do not merely shrink, they vanish completely. And this is precisely why the breakthrough we've been tracing was built to stay below light speed. It was never a disappointing compromise, it was survival. A subliminal warp drive does not break the barrier, but it does not roast its crew, or sterilize its destination, or threaten the order of cause and effect either. And there is a deeper, stranger thought folded inside all of this, one that Stephen Hawking himself reached for. He proposed what he called the chronology protection conjecture, the idea that whenever the laws of physics seem to open a door to time travel, nature will always find some mechanism to slam that door shut before anyone can walk through it. And some physicists have wondered whether the warp bubble's self-destruction, that front wall cooking itself into oblivion the instant it outruns light, might be precisely that mechanism in action, the universe's own immune system, a reality that quietly vaporizes any vessel reckless enough to try to break time before the paradox can ever be born. So the faster-than-light dream, the one our title set out to chase, looks less and less like a doorway to the stars, and more like a loaded gun, pointed at the traveller and at the logic of the cosmos itself. The subliminal drive survives, but it never breaks the wall. It only slips quietly around its edge, which forces us back, one more time, to the question we have been circling since the very beginning. If wrapping space around yourself turns lethal the moment you try to truly outrun light, then is there another way through? A different door entirely? Not a bubble that carries you around the vast distance, but a tunnel that pierces straight through it, joining two far-flung points of the universe and letting you step across the gap as though it were a single pace. Physicists have studied that second doorway for nearly 100 years, and when we open it, we will find ourselves standing once again, face to face with the one ghost this story has never managed to escape, the same impossible substance that poisoned the very first equation all those years ago. Negative energy. It has been waiting for us the entire time. So picture the other road, Not a bubble that wraps itself around you and drags a piece of space along for the ride, but something stranger and, in a way, simpler. A tunnel, a shortcut bored straight through the fabric of the universe, joining two places that might be separated by thousands of light years, and letting you step from one to the other as though you were merely crossing a room. If space is too vast to cross, then perhaps you do not cross it at all. Perhaps you go through it. And this idea, this second doorway, is not new. It is older than the warp drive by 60 years, and it leads, in the end, to the very same locked vault. So let us follow it and see where it breaks. The tunnel was first glimpsed not by a dreamer, but by Einstein himself. In 1935, working alongside a physicist named Nathan Rosen, Albert Einstein published a paper in the journal Physical Review with a dry, forgettable title, The Particle Problem in the General Theory of Relativity. He was not trying to build a starship, he was trying to understand the nature of particles. But buried inside the mathematics, the two of them found something extraordinary. A structure hidden in Einstein's own equations that connected two entirely separate regions of space-time, joined at a kind of bridge. We remember it today by their names, the Einstein-Rosen bridge. For a moment, it looked like a door between worlds, but the door had a fatal flaw, because that original bridge is a death trap. Run the mathematics forward in time, and the tunnel does something violent. It pinches itself shut, and not slowly. It collapses so fast that not even light, the fastest thing in existence, could make it from one end to the other before the walls slammed together. Anything caught inside would be crushed into oblivion. For decades after, the bridge remained exactly that, a curiosity in a textbook, a quirk of the equations that nature seemed to have built and then bolted shut. The physicist John Wheeler would later give these structures the name we use now, wormholes. But a name was all they were. A tunnel you could never survive is not a route, it is a tomb. And there the idea sat, locked, for more than half a century, until 1988, and the turn came from the most unlikely place imaginable. Not a laboratory, a novel. The astronomer Carl Sagan was writing a work of fiction, his book Contact, and he wanted to send his heroine across the galaxy in a way that real physics would not laugh at. So he did something most novelists never would. He called a physicist. He reached out to Kip Thorne at the California Institute of Technology, one of the great minds in the study of gravity, and asked him a simple question: could there be a way through? Thorne, together with his student Michael Morris, took the question seriously, and what they produced changed the entire field. In a paper published in the American Journal of Physics, volume 56, with the almost academic title Wormholes in Space-Time and Their Use for Interstellar Travel, Morris and Thorne laid out a new class of solutions to Einstein's equations, wormholes that, unlike Einstein and Rosen's death trap, might actually be crossed by a living human being. The traversable wormhole was born. Here is the way to see it. Take a flat sheet of paper and imagine two dots drawn at opposite ends. Normally, to travel from one dot to the other, you must move all the way across the surface. But now fold the paper so the two dots touch. Punch a single hole straight through where they meet, and suddenly the two distant points are joined by a passage far shorter than the journey across the page. That fold, that puncture, is the wormhole, and the beauty of it is the same quiet trick the warp drive used. Inside the tunnel, you never break the speed of light. You drift through the throat slower than a beam of light moving beside you. But because the throat itself is a shortcut, you arrive at the far end long before any light that took the long way around. You never outrun light. You simply take a road light does not know about. For a moment, imagine you are there, drifting toward the mouth of such a tunnel. Ahead of you, you would not see darkness, but a strange circular window hanging in space, like the shimmering surface of a soap bubble, and through it, impossibly, the stars of a completely different region of the sky, smeared and bent around the rim of the opening. As you slipped inside, that distant starfield would swell and then steady until you emerged beneath a sky that the nearest beam of natural light would still need thousands of years to reach. One step, an entire arm of the galaxy, skipped. But a road you can survive comes with conditions, and the conditions are brutal. Morris and Thorne worked out exactly what a traversable wormhole would demand. First, no event horizon. A black hole has one of those, a point of no return, a boundary you can fall past but never climb back out of. A usable tunnel can have none of that. You must be able to enter, cross, and emerge. Second, the throat must be wide enough that the tidal forces of gravity would not rip a human body apart on the way through, which means a passage perhaps kilometers across, a mile or more wide, not some microscopic pinhole. Third, the crossing must take a sensible amount of time. And fourth, the hardest of all, something has to hold the tunnel open, because gravity hates a wormhole. Gravity wants always to pull that throat closed, to crush it back into nothing, exactly as it crushed the Einstein-Rosen bridge. When Morris and Thorne worked out what kind of material could resist that pull, the answer was staggering. The stuff lining the throat would need to be held under a tension more extreme than the crushing pressure at the very heart of the densest neutron star, a star so compressed that a single sugar cube of it would weigh as much as a mountain. And it gets stranger still. That tension would have to be so enormous it exceeded the material's own mass energy, a property no ordinary substance in the universe possesses. The only thing in all of physics that could push outward hard enough against the relentless inward pull is matter with negative energy density. Exotic matter, the same impossible ghost that haunted every warp drive we have followed. And for the wormhole, the curse runs even deeper. Because here, the negative energy is not a fuel you spend once to get moving. It is structural. It is the load-bearing pillar holding up the entire tunnel. Every single second you are inside it. Remove it for 1 instant, and the tunnel does not sag. It snaps shut. It crushes. Gone. You would not merely lose your engine. The walls would come down on you, mid-crossing, in the dark. Light years from anywhere, and it gets worse, because the same nightmare from before returns. Morris and Thorne, now joined by a third physicist, Ulvi Yurtseva, showed in a follow-up paper that a wormhole too could be turned into a time machine. The same closed loops in time, the same paradoxes of cause and effect arriving before their causes. The tunnel through space was also, potentially, a tunnel through time, dragging all of its impossible consequences along with it. And even if you could somehow gather the exotic matter, there waits one more blow. Most of the wormhole geometries physicists have studied turn out to be violently unstable. A single stray particle, a faint ripple in the surrounding space, the smallest disturbance imaginable, and the whole structure tears itself apart. Some later researchers have explored whether reaching into extra dimensions of space or rewriting the rules of gravity itself might let a tunnel hold open with less of the forbidden matter, or perhaps none at all. But that work remains deeply speculative, and as for tunnels forming on their own, naturally, somewhere out in the cosmos, the consensus is that genuine traversable wormholes are extraordinarily unlikely to exist anywhere in the real universe. So step back and look at what we have found. 2 doors, the warp bubble and the wormhole, 2 completely different roads to the stars, and both of them slam shut against the exact same wall. Both roads end in the same place. The warp bubble needs it, the wormhole needs it, the same ghost. Always negative energy. Every path we have walked, every clever solution, every shrinking number, every fold in space, dead ends at one single question we have been quietly carrying since the very beginning and can no longer avoid. can negative energy actually exist? Not as a symbol in an equation, not as a theorist's convenience. Truly physically in the real world, can you make it, hold it, point to it? And here, at last, the universe gives us something. Not everything, but not nothing either. The answer is a phenomenon called the Casimir effect. In 1948, a Dutch physicist named Hendrik Casimir, working at the Philips Research Laboratories in the Netherlands, the research arm of the very company that made light bulbs and radios, was puzzling over a problem when a conversation with the great Niels Bohr pointed him toward an answer. Bohr suggested the thing he was chasing had something to do with zero-point energy, the strange, restless energy of empty space itself, and from that hint, Casimir predicted something genuinely bizarre. Take two flat metal plates, completely uncharged, and bring them extraordinarily close together in a vacuum, closer than a fraction of the width of a human hair, and they will feel a faint force pulling them toward each other, a pull coming from nothing, a pull coming from the vacuum. To understand why, you have to abandon the idea that empty space is empty. It is not. Down at the smallest scales, the vacuum seethes, a restless ocean of fluctuations, waves of every possible size flickering in and out of existence. Now, slide two plates close together. In the narrow gap between them, only certain waves fit, the ones whose size matches the space. The larger waves are simply locked out, shut at the door, and so the region between the plates ends up holding slightly less of this vacuum energy than the open space outside. Less than empty, emptier than nothing. And that strange, suppressed pocket between the plates carries genuine negative energy density, real, measurable, the forbidden substance sitting quietly in the gap. For a long time, that was still just theory on a page, but then it was measured. In 1997, a physicist named Steve Lamoureux, then at the University of Washington in Seattle, built the experiment for real. He took surfaces coated in copper and gold, mounted one on a delicate torsion pendulum, a horizontal bar hung from a thin fiber, so sensitive it could feel the faintest twist, and brought them together within a few millionths of a meter, and the plates pulled toward each other, precisely as Casimir had predicted more than 4 decades earlier, to within about 5% of the theory. The negative energy of the vacuum was no longer a guess. Someone had felt it move, and the story did not stop there, because in 2011, at Chalmers University of Technology in Sweden, researchers pushed the idea to something close to magic. Using a superconducting circuit as a kind of mirror, they effectively waved that mirror back and forth through the vacuum at nearly the speed of light, and out of the empty darkness, real photons appeared. Actual particles of light, conjured from apparently nothing, torn loose from the vacuum by the violent motion. They had reached into the emptiness and pulled out light. And here is the detail that ties this entire journey into a single thread. At the very end of his original 1994 paper, the one that started this whole modern dream, Miguel Alcubierre himself pointed directly at the Casimir effect, suggesting that the negative energy of the vacuum, the very thing Casimir had found, might one day power his warp drive. Both doors, the bubble and the tunnel, reaching, across decades, for the very same key. So we have it. Negative energy is real. We have measured it. We have held it in a laboratory. The vault is not empty after all. But before the hope rises too high, here is where it meets the wall, because the amount of negative energy the Casimir effect produces is vanishingly, almost incomprehensibly small, a faint whisper in a gap thinner than a hair, and the quantity a warp drive or a wormhole would demand is so far beyond it, separated by so many orders of magnitude, that the distance between what we can make and what we would need is difficult even to put into honest words. We have a single drop. The ocean required is almost beyond imagining, and then comes the deepest constraint of all. one that may be woven into the laws of physics themselves. Two physicists, Lawrence Ford of Tufts University and Thomas Roman, spent years studying how negative energy is allowed to behave, and what they uncovered in a set of principles now called the quantum inequalities reads almost like a law of cosmic accounting. Negative energy is permitted to exist, but the universe polices it without mercy. The more intense the negative energy you try to gather, the shorter the time it is allowed to last, and the smaller the region it is allowed to fill. Concentrate it, and it vanishes faster. Spread it out in time, and it must grow fainter. Think of the vacuum as a ruthless lender. It will hand you negative energy, yes, but the larger the loan, the more violently and the more quickly it is called back in. And for a wormhole, Ford and Roman found something close to damning. The negative energy needed to hold the throat open would have to be squeezed into a shell many, many times thinner than the tunnel itself, a band so impossibly thin that building a wormhole large enough for a human to pass through begins to look, by the universe's own rules, almost forbidden. So this is where every road has finally carried us. We can shrink the warp bubble until it is almost reasonable. We can draw the wormhole in precise mathematical detail. We can even reach into the empty vacuum and pull out a genuine flake of the forbidden substance with our own instruments. And yet the chasm between that flake and what either door truly demands is so vast that crossing it may require something we do not yet possess. Physics beyond the standard model, beyond the confirmed laws, beyond the edge of everything we currently know to be true. And so, after all of it, the breakthroughs and the shrinking numbers, the lethal dangers and the two impossible doors, the single ghost that has shadowed every step, we arrive at the only question left that truly matters, the honest one, stripped of the romance and stripped of the despair. After everything science has genuinely discovered and everything it still cannot do, where does this actually leave us? Have we, in any real sense, cracked it? Or have we only learned in greater and more breathtaking detail exactly why the door remains closed? And so we arrive at the only honest thing left to do, to stop dreaming for a moment and start accounting, to lay everything we have gathered on the table, the breakthroughs and the dangers, the shrinking numbers and the stubborn ghost, and ask plainly where it truly leaves us. But the accounting opens with a surprise, a sign of just how far this once impossible dream has actually travelled, because warp drives have now crossed a threshold that fantasies never reach. Scientists can model one so precisely that they can predict exactly what it would look like if it died. In 2024, a physicist named Katie Clough at Queen Mary University of London, working with Tim Dietrich in Potsdam and Sebastian Kahn at Cardiff University, published a study with a title that says everything: what no one has seen before, gravitational waveforms from warp drive collapse. And there is a quiet poetry in where it came from, because Sebastian Kahn works at Cardiff, the same university where Miguel Alcubierre first dreamed up the warp drive 30 years earlier. The torch had been carried all the way back to where it was lit. Here is what they did. Remember that a warp bubble depends entirely on that exotic matter to hold its shape, the structural pillar we spoke of, the thing keeping the walls from caving in. So they asked a simple, almost morbid question. What happens if that containment fails? If the bubble loses its grip and collapses? Using numerical relativity, running Einstein's actual equations forward inside a supercomputer, step by step, they simulated that collapse, and they found something remarkable. A dying warp bubble does not simply vanish, it screams. As it caves in, it sends out a sharp, distinct burst of gravitational waves, ripples in the fabric of space-time itself, the very same kind of waves that the LIGO Observatory first caught in 2015 from two black holes colliding 1 billion light-years away. That detection was a landmark in its own right, the first time in all of human history that anyone had directly felt a tremor in space-time, a ripple Einstein had predicted a full century earlier and quietly doubted we would ever be able to measure. And the simulation uncovered something even stranger about the nature of that burst. The collapsing exotic matter first hurls out a wave of negative energy, the forbidden substance itself flung outward into space, followed by an alternating train of positive and negative waves, rolling out one after another like the swells behind a passing ship. Stranger still, the whole violent process ends with a net increase in the total energy of the system, as though the collapse had somehow conjured something out of its own wreckage. But this particular scream has a strange pitch, and that pitch is the whole story. From a warp bubble roughly a kilometre across, call it a little over half a mile, the collapse would ring out at a frequency near 300,000 cycles per second. Now, to understand why that matters, you have to know what our detectors can actually hear. LIGO and the gravitational wave observatories we have today are tuned to a low range, from a few times a second up to a few thousand, which happens to fall roughly within the range of human hearing. 300,000 cycles per second sits far, far above that, like a dog whistle pitched so high that no human ear and no instrument we currently operate could ever catch it. So our existing detectors would hear nothing at all. The starship could die, and we would be deaf to it. Except, and this is the door left open, future detectors, tuned to those much higher frequencies, could in principle catch it. No such instrument has been funded yet, but the researchers were careful to point out that the technology to build one already exists. We could, if we chose to, build an ear for exactly this, and that cracks open two possibilities that are genuinely staggering. The first is a wholly new way to search for life among the stars. For decades, our search for alien civilizations has meant listening for their radio broadcasts, straining for a signal in the noise. But consider this instead. If any civilization, anywhere in the galaxy, across all of cosmic history, ever built a warp drive, and if even one of those drives ever failed, the death cry of that collapsing bubble would go rippling outward through space-time, a gravitational wave that might, one distant day, wash over the Earth. We would not be listening for their words. We would be listening for the collapse of their starships, a search for alien technology written not in radio, but in the trembling of space itself. The second possibility is quieter, but in its own way just as profound. Because in learning to model these strange space-times, these regions of warped negative energy, physicists are sharpening tools that reach far beyond the warp drive. The very same mathematics illuminates the violent hearts of black holes, the behavior of matter under impossible conditions, even the birth of the universe. The dream, though no one has built it, is already paying for itself in understanding. So this is no longer idle fantasy. This is a research program producing real, testable predictions, and that fact alone should reframe the entire question. So now, with all of it gathered, the honest reckoning. Strip away the wonder. Strip away the dread. What does the mathematics actually permit, right now, in this moment? The answer comes in three parts, and they are not the same answer. Yes, warp spacetimes are genuine, valid solutions to Einstein's equations. This was never crankery or science fiction dressed up in symbols. The geometry is real, bends space the right way, and the mathematics holds together perfectly. Yes, again. And this is the true breakthrough at the center of everything we have followed. A warp drive that stays below the speed of light may, in fact, be possible using nothing but ordinary, positive energy. No exotic matter, no forbidden ghost at all. The team at Applied Physics built exactly such a solution, a subliminal warp effect that by their analysis breaks none of the universe's sacred energy rules. On paper, the impossible had become merely difficult, but still no. True faster-than-light travel, the kind that needs no negative energy, remains unproven, and the obstacles, far from clearing, have been mounting. And here is where the field genuinely splits into a real, unresolved scientific fight, the kind that does not get settled in a single paper. Because the instant anyone claims a positive energy warp drive, a group of skeptics raises an objection that is subtle and quietly devastating. In 2022, 3 physicists, Jessica Santiago, Sebastian Schuster, and Matt Visser, pointed out something easy to miss. A warp drive might look perfectly positive, perfectly safe to one observer, the one riding comfortably along inside the bubble. But physics does not grade on the view from a single seat. Its true rule demands that every possible observer, including those flying through the bubble at different speeds and angles, must also see allowed, honest energy. The most basic of these rules even carries a name, the null energy condition, and it asks for almost nothing, merely that no observer, not even one racing along at the speed of light, should ever find the energy in a patch of space dropping below zero. It is about the gentlest demand physics knows how to make, and warp drives, the critics showed, break even that, and the problem appears to run deeper than mere speed. Earlier analysis had already revealed that the warp geometry tends to violate these rules even when the bubble crawls along far below light speed, which suggests the trouble is woven into the very shape of the thing, not merely into the reckless act of trying to outrun light. So by that stricter standard, Santiago and his colleagues argued, all physically reasonable warp drives still violate the energy conditions. The ghost was not gone. It was merely hiding from the passenger in the best seat. And that critique is not a dusty old argument. It is alive, right now. Because in 2026, a researcher named Anne Thiele built a new computational toolkit designed to do exactly what the skeptics demanded, to check a warp space-time against every conceivable observer at once, robustly, leaving nowhere for the forbidden energy to hide. And when that toolkit was turned on the promising new subluminal solutions, it still found violations. Small ones, but real ones. Other recent work tells the same cautious story. In a 2025 peer-reviewed study, the physicist José Rodal described a warp geometry whose energy is overwhelmingly positive, a genuine step forward, and yet he too was forced to admit a small, stubborn remainder of negative energy that simply refused to fall all the way to zero. So the honest picture, as of today, is unsettled. One camp keeps building better and better positive energy designs. The other keeps discovering that the negative energy, however much we shrink it, however cleverly we hide it, stubbornly refuses to vanish entirely. The debate is not won. Not yet. And beneath every layer of this, the deepest question remains genuinely, completely open. Negative energy is real. We have measured it, held it in a laboratory, pulled photons from the empty vacuum. But can it ever be scaled up, concentrated, sustained, and held at anything remotely close to the monstrous levels a true warp drive or a human-sized wormhole would demand? Nobody knows, and the most honest answer anyone can give is that doing so may require physics we have not yet discovered, laws lying somewhere beyond the standard model, beyond the furthest edge of everything we currently understand to be true. So the gap is closing, but it is closing in understanding, not yet in building. We grasp the warp drive today with a depth and precision that Miguel Alcubierre, scribbling his idea in 1994, could not have imagined. We can simulate these bubbles, we can classify them, we can predict the gravitational cry of their collapse and dream of instruments to hear it, but the energy to power one, the materials to construct one, the machines to test one, those remain, by every sober estimate, centuries beyond our reach. So, the question the title asked at the very beginning of all this, have scientists finally cracked how to travel faster than light? The honest answer is no, not faster than light, not yet. But that no is not the same no we began with, because something fundamental has shifted beneath our feet. For most of a century, the warp drive lived in the land of fantasy, and fantasy means a thing that violates the laws of physics, a thing the universe simply forbids. What the work of the last few years has quietly done is carry the warp drive out of that land altogether, not into reality, not yet, but into an entirely different category, an engineering problem. And the distance between those two things is the distance between impossible and merely unbuilt. A fantasy asks the universe to break its own rules. An engineering problem only waits for us to catch up. So let us say it as plainly and as truthfully as it can be said. Scientists have not cracked faster than light travel. What they have cracked is something quieter and stranger, and in its own way no less extraordinary, a warp effect that the laws of physics, as best we can currently tell, might actually allow. Think back to the wall we started with, the barrier of light speed, and the door set into it, bolted shut, the door that Einstein himself seemed to have locked, and locked forever. For 100 years, that door did not so much as tremble. We are not through it. We may not pass through it for centuries, perhaps not ever, but for the first time since Einstein turned the key, the bolt has shifted in its housing. The door once thought sealed now stands, ever so faintly, quietly ajar, and a sliver of light is coming through. And yet, tonight, none of this moves the stars 1 inch closer. Proxima Centauri still burns exactly where it has always burned, around 25 trillion miles away, 40 trillion kilometers, and Voyager 1, that lonely probe we began this whole journey beside, the fastest object our species has ever flung into the dark, would still need something like 70,000 years to limp across that gulf. The numbers on the page have not changed at all, but here is the thing about the creatures asking the question. This is a species that, only a few years ago, reached across the darkness with a planet-sized web of telescopes and took a photograph of a black hole, a thing woven from pure gravity that not even light can escape, and turn the single most unimaginable object in the cosmos into a picture you could hold on a screen. A species that built machines able to feel a ripple in space-time 1,000 times smaller than the nucleus of an atom. We are not, it turns out, a people who are easily frightened by large numbers. The equations are already written, the simulations already run. What stands between us and the stars is no longer a question of whether the universe forbids the journey, but only whether we have the patience to close the long, slow distance between knowing a thing and doing it, one discovery at a time. The instruments are waiting to be built, the materials are waiting to be found, and somewhere, perhaps in a century none of us will live to see, the first faint bubble of gently bent space may quietly take shape on a laboratory bench, small and dim and almost nothing at all. A flicker, a first, undeniable spark. The stars remain distant tonight, but for the first time in the long history of this question, they are no longer mathematically forbidden. The door Einstein seemed to seal is no longer fully closed, and a species that taught itself to map the shape of space-time can afford to be patient. One equation, one bubble, one quiet century at a time. Take all of it away, the bubbles, the negative energy, the equations that almost worked, and the ones that never will. Set the whole machine down for a moment and look at what is left underneath. A want, nothing more than that. A quiet, stubborn ache to be somewhere you cannot reach. People felt it long before they had the mathematics to chase it, before cities, before writing, before we even had names for the stars. They stood in the dark, looked up at those small, cold lights, and felt the pull to cross to them, and the distance always said no. Tonight, the warp drive is only the newest shape of that very old longing, the same ache wearing the clothes of physics, And maybe that was the real answer all along. Not whether we can go, but what kind of creature stares at a sealed door for 100,000 years and keeps gently reaching for the bolt. That reaching is you. It may be the most human thing you will ever own. Thank you for walking this long road with me tonight. If it stayed with you, a like and a subscribe is how you tell me to keep going. Quieter journeys are still coming. I hope you will be there. The door is not open, but it is no longer locked, and that quiet, impossible wanting will still be there in the morning. It always is. Good night.